Hey guys, so I wanted to go over just a few little details today before I got started. I have a marker board here. Hopefully, you can see this. But I wanted to bring to your attention that we have some rules here. If I have g of x is equal to a times b raised to the x power, whatever happens to this a is going to determine whatever the value is of this a. That's going to determine if my graph is being stretched vertically or if it's being compressed vertically. So this determines vertical stretch or a vertical compression. I'm going to abbreviate here, vertical compression. So if this value of A is greater than 1, then it's being stretched vertically. It's making it taller. If that value of A is less than 1, then it's compressing it vertically. Okay, then the other function that we have to consider is when we have B raised to the AX power. So I have the letter B being raised to the power. So then this A determines if it's a horizontal compression or if it's being stretched horizontally. All of this is in the middle of the page 500. It explains this, but I just kind of wanted to go over it in case you didn't read it. So if A is 1/2, then that means it's going to be vertically compressed. It's going to get wider. If if A is greater than 1, then it's going to get stretched vertically. It's going to get taller. And then if I have B raised to the AX and A is greater than 1, then it gets compressed horizontally. And if B is horizontally, and if A is between, it's actually the absolute value of A is between 0 and 1, then it's going to get stretched horizontally. So that was just some notes I wanted to make sure that you took or you read, you heard something so that you were aware of this. So we're going to look at example 7 in your workbooks, and it's talking about horizontal dilations of exponential functions. So let me make me a little smaller here. We're going to look at this. So if I am looking at the function 5/3 raised to the 2x and comparing that to the parent function 5/3 raised to the x. So we're not really paying attention to the 5/3. We're looking at the exponent part. So on the parent function, it's raised to the x, but on g of x, it's been raised to the 2x. So if you think back to what we just discussed, this is going to either be a horizontal compression or it's going to be stretched horizontally because we're looking at this part where it's raised to the 2 times x. So since it's greater than 1, that tells me that it's compressing my graph horizontally. So if you want to fill in your workbook, it says x is multiplied by the positive constant a before it has been evaluated. And the absolute value of A is greater than 1. That's this part right here. The absolute value of A is greater than 1. So the graph is compressed horizontally by a factor of 1 over A. And in this case, our A was 2. So it's been compressed by a factor of 1/2. So hopefully that makes sense. We're not really even doing math. We're learning how to we are doing math, but we're not doing computations. We're looking at the function and figuring out what it should look like just by looking at it rather than having to think, rather than having to create tables and things like that. We're just looking at the equation saying, oh, well, that power there is being multiplied by a 2, so I know that it is going to be compressed horizontally. All right, so example number 8, the bottom of page 501, says energy. Since 2000, solar PV capacity in the world has been growing exponentially. So as soon as I hear the words growing, erase some of this, I know that my graph should look like this. That's beautiful. Ta-da! We have a horizontal asymptote down here. This is probably at 0, 1, where it's crossing the y-axis, just assuming. But I don't know that for sure. But it is growing exponentially. So let's continue reading. And it can be approximated by the function c of x equals 0.897 times 1.46 raised to the x, where c of x is the solar PV capacity in gigawatts, x is the number of years since 2000, and 0.897 is the initial capacity. So describe the dilation in c of x equals blah, 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 as it is related to the parent function f of x equals blah, blah, blah. So look at what happened at the differences there. The difference is the number being multiplied in c of x is between 0 and 1. It's 0.897. So my function is being multiplied by an a value that's in between 0 and 1. So I immediately know something's happened horizontally because it's not on the power. I'm sorry, vertically, because it's not on the power. If it was on the power, it'd be horizontally. So since it's being multiplied by the number, it's either stretching vertically or compressing vertically. And since that number is between 0 and 1, that lets me know that it's being compressed vertically. So looking at this, we're going to fill in the blanks. It says the parent function f of x equals 1.46 raised to the x. Then c of x equals a times f of x, where a is equal to 0.897. Okay, so moving on down. C of x equals 0.897 times 1.46 raised to the f. So therefore, C of x is equal to 0.897 times x. So the function is multiplied by the positive constant a. Once again, that positive constant a is being multiplied after it has been evaluated, and the absolute value is between 0 and 1. So the function f of x is being vertically compressed or compressed vertically by a factor of 0.897. So one more time, because this was when I wrote it out here to begin with, we're multiplying it in front of our function. It's a vertical compression or stretched vertically. But we know that since that value is between 0 and 1, that makes it a vertical compression. That value is 0.897. So it's between 0 and 1, so it's compressed vertically. Okay, moving on to example number 9. Are we having fun yet? Example 9. Moving right along. Identify exponential functions from graphs and dilations. Okay, so the given graph is a dilation of the parent function. Notice that every point on the graph of g of x is closer to the x-axis, implying a vertical compression of the form g of x equals a times 2 to the x. So the point 2, 1 lies on the graph. Is everybody here with me? So we're going to substitute the coordinates in for x and y to solve for a. Dun, dun, dun. Okay, so once again, we're going to look at that point at 0, 1. On the parent function, it's at 0, 1, but look at how it shifted. It shifted over 1, 2 places. So we can see that our graph passes through the point 2, 1. So back to using that equation, y equals a times b raised to the ax. We don't know what a is, but we know that our b is 2. Okay, so the next thing that we know, well, actually, that came from right here. The f of x equals 2 to the x. So knowing that it passed through that point when x is 2, y was 1, we can plug that in. So let me write this down again. I'm not very good at just talking and not showing. So I have y equals a times b raised to the ax. Erase this. Okay, so I don't know what this value of a is, but I do know that the b is 2 because of the parent function. It told me that in the equation. I don't know what this value of a times x is necessarily, but I know that x is 2, so I'm going to plug in a 2, when y is 1, so I'm going to plug in my 1. Well, we can evaluate this. 2 squared is 4. So I have 1 equals a times 4. Okay. I need to get a by itself. So if a is being multiplied by 4, to get rid of that, I divide by 4. 4 over 4 is 1. That cancels. So 1, divide this side by 4. 1 over 4 is nothing more than 1/4. So my a is 1/4. So knowing that a is 1/4, that tells me, and we could actually see that also by looking at the graph, that it is a vertical compression. And my equation would be then y equals 1/4 times 2 raised to the x power. This is a lot harder than it looks to write like this. All right, and now we're moving on to example number 10. Example 10 says vertical reflections. Reflections are fun. If I multiply something by -1, that's going to flip it over the x-axis. So if we look at -3 times 2 raised to the x and how it's related to the parent function of 2 raised to the x, then we can quickly see that it has been just flipped across the x-axis, and then the fact that it's being multiplied by a 3 is stretching it vertically. So we stretch it vertically and we flip it across the x-axis. So, one more time, let's fill in the blanks. The function is multiplied by -1 and the positive constant a after it has been evaluated. And the absolute value of a is greater than 1. So the graph of f of x equals 2 to the x is stretched vertically and reflected across the x-axis. And those are the blanks you had to fill in. And number 11, example number 11, we're on page 503. Says describe the reflection in g of x equals 3 raised to the -2x power as it relates to the graph of the parent function f of x equals 3 raised to the x. So if you look at what happened in the graph, let me pull that graph up here real quick. There we go. If you look at this, it has flipped. You can see it's flipped across the y-axis this time, and it's closer to the y-axis. So that tells me that it's being stretched vertically. Okay, so the function is multiplied by -1. And the constant a before it is evaluated, and the absolute value of a is greater than 1. So the graph is compressed horizontally and reflected across the y-axis. Okay. So this stuff's a little bit weird. It's kind of, you just have to memorize it. I mean, it reiterates some of the rules that we learned early on. If you're shifting a line up or down, you're adding or subtracting from the y-intercept. If you're shifting a line left or right, you're doing that in the parentheses to the values of x. It's reiterating the same things that you've already learned with quadratics, that you've already learned with linear equations, you learned with absolute value functions, and now we're doing it with exponential functions. All of these tie in together. So if you didn't learn it then, you've got an extra chance now to work on it. All right, and our last example for transforming exponential functions is example number 12. So it says multiply transformations of exponential functions. Describe how the graph is related to the graph of the parent function. So we're going to move through these steps to see how the two are related. we can tell that it's flipped, flipped across the y-axis, or x-axis. So what's going to happen that's going to make it flip across the y-axis? Says since f of x equals 3 raised to the x, g of x is equal to a times f of x minus h plus k, where a equals a negative 1/2, given to us up here in this equation. And since a is less than 0 and the absolute value of a falls between 0 and 1, the graph is reflected across the x-axis and it's compressed vertically by a factor of 1/2. Okay, then we know that since there's an h equal to 2, that h is greater than 0, so that takes our graph and translate it h units to the right, or 2 units to the right once it's been flipped. Oops, I skipped one. And then last of all, our k is -1. So since our k is -1, that translates it down 1 unit. That was a lot of transformations. It took the parent function and compressed it vertically, reflected it across the x-axis, and translated 2 units right and 1 unit down. Once again, you might want to just read over these notes in your workbook. There's some great things to take note of in the middle of page 500. We did talk about it, but you might want to read over it again. And there at the bottom of page 502, there's some more rules. And then again at the top of 504, each little section where it says learn, you might want to go back and read that to try to help yourself better understand these rules and what's happening before you start your assignment. And this sums up week 1. I will see you guys Thursday.